All right, now we're going to talk about how to find the slope of a line that's tangent to a curve. The concept of a tangent line is really pretty simple visually, geometrically, and we're going to take what we learned in the last section with the limit, defining the limit of a function, to help us figure out what the slope of a tangent line is. So let's start by looking at this function. It's a function of x squared plus 1, so it's a nice parabola. It's a nice smooth curve. We could sort of see, we could tell visually it's continuous everywhere. And what we want to do is find a way to describe the slope. Now, of course, the slope of a curve seems like an odd thing to say, like an odd phrase, because of course it doesn't have a constant slope, right? Like sometimes it's decreasing, sometimes it's increasing. But while we don't have like a constant slope for a curve, we still want to find a way to describe in a precise way how it changes. In a more precise way than simply saying, well, it's decreasing over for the negative values and increasing over for the positive values. And the way that we're going to do this is to find a slope of a tangent line. So if we find a slope of a line that's tangent to a curve at a particular point, that'll tell us how the curve is changing right at that point. So let's begin. Let's take a look. Here's the same function, and let's focus on this point here at, say, 2, 5. I'll call this point P. And the tangent line I can draw. A tangent line is by definition a line that touches the curve just at that one point. So we can draw this tangent line pretty easily, right? And as far as determining its slope, really the best I can do is say, well, it looks like it's increasing. So it looks like we still don't quite have a way to find that slope yet. The problem we run into is that in order to find the slope of a line, we need 2 points in order to use rise over run. And we have just a single point. So in order to help us build this tangent slope, in order to get closer to it, we're going to start by approximating it. We're going to approximate the slope by drawing what we call a secant line. So here's our point. So this is the same graph. This is y equals x squared plus 1. I've just sort of zoomed in on the first quadrant region. And here's the point we're interested in here at 2, 5. We're going to call this point P. And now I'm going to pick another point. I'm going to pick this point up here on the curve. I'm going to call it Q. It has arbitrary coordinates x, y. Like, I am not picking a particular point on the curve. I'm just saying it's definitely on the curve. And if it's definitely on the curve, then if the x coordinate is x, the y coordinate has to be x squared plus 1 because it's on the curve defined by that equation. And the secant line is the line I get by connecting these 2 points on the curve. Right, so this is a secant line. It is definitely not the tangent line, right? Like, I know that the tangent line kind of looks like this. Maybe that's a little bit off. Looks a little bit more like this. Okay, but we can approximate by using a secant line. And the closer this point Q gets to the point P, the closer that secant line becomes to being the actual tangent line. So I think of this point Q as like a free point that kind of slides up and down the curve, and I want to push it closer and closer. I want to push it down the curve so that it gets closer to P. Before we do that, first we're just going to get an expression for the slope of that secant line. So the slope of the line connecting points P and Q, rise over run, let's see, the y coordinate, I'll treat point Q like it's my x2, y2, so that's on top we have x squared plus 1 minus 5. On the bottom, x minus 2 And if we simplify, we've got x squared minus 4 over x minus 2. So for any point Q that I might pick for that second point on the curve, the slope will be given by this fraction right here. Now what we want to do in order to find the tangent slope is we want to use just a single point, right? Like we only want to have that point P. Now of course if Q is equal to P, then we'd be dividing by 0, right? Then on the bottom we'd have 2 minus 2, and we can't divide by 0. But what we can do is slide Q closer and closer to P as close as we can, and that is of course a limit. So the slope of the tangent line is actually defined by taking that limit as Q approaches P. And we're going to call this tangent slope M tan. This is the limit as x approaches 2 of the slope formula that we found up here, x squared minus 4 over x minus 2. And now we're going to use what we learned in the last section to evaluate this limit. We can't let x equal 2 right off because we divide by 0, but we can factor the numerator. We can cancel out the x minus 2. So now we have the limit as x approaches 2 of x plus 2, and that gives us 4. So there's the slope of the tangent line. Now we know precisely how this function is changing when x is equal to 2. It is increasing with a slope of 4 at the point 2,5. So we could use this same technique to find the slope of a tangent line at any point on this curve and expand that to other curves as well. But I'll just note that right now, the way we've set it up, if I wanted to find the slope of the tangent line at a different point, at the point 1, 2, or at the point 3, 10, I'd have to set up a new limit, right? Because our point P would be changing. But another option we have is to define the slope of a line that's tangent at an arbitrary point. Right now, this is important. The first thing I'm going to do is fix a little typo. I would guess, I don't know if it's a typo since it happened when I was writing something out by hand, but this point Q, I mistakenly wrote the x coordinate as x right here, and it is x plus h. So that's the point Q right there. So here's the idea. We have a point that we're interested in. This time we're not going to specify what the point is, just that it's on the curve of y equals f of x. So our point P is the point x, f of x. The way that I'm going to obtain that second point Q is I'm just going to move up by h. You know, like I'm just using h to be the amount, like sort of the step amount that I'm moving my x coordinate. So the x coordinate here is now x plus h, and the y coordinate is f of x plus h. The secant slope is f of x plus h minus f of x. There's your change in y's. On the bottom, we have the change in x's is x plus h minus x, which is h. So just using the rise over run, we get this secant slope in this fraction. And if I want the tangent slope, if I want to slide Q closer and closer to P, then what I'm actually doing is sliding this point x plus h closer and closer to x, so that this distance h is approaching 0. That's how I slide Q closer and closer to P. And so the slope of the tangent line is this limit as x approaches, is this limit as h approaches 0 of f of x plus h minus f of x, all divided by h. The tangent slope is also called the instantaneous rate of change of f of x with respect to x. So how it is changing at that very instant, at that singular point. So we're going to take some time and find some tangent slopes. And the way we're going to do it is we're going to find an expression for the slope of a tangent line. So we're going to set up the limit, and when we evaluate it, the result isn't going to be just a number. It's going to be some expression with x, and we could use that expression to find the actual tangent slopes at as many points as we want. So in this function, in this example, our function is y equals 4x minus x squared. And so that's our f of x. Now, I know that I'm going to have to evaluate this limit here on the other page. So that means I need to get an expression for f of x plus h. And then I'm going to have to put that together to get an expression for f of x plus h minus f of x to figure out what goes in the numerator. So let's kind of build this up. If that's our f of x, then f of x plus h. I'm going to replace x with x plus h, right? Just this function notation. So this is 4 times x plus h minus x plus h squared. We got to be careful with our algebra. We can distribute that 4, so we have 4x plus 4h minus, and now I'm going to square out the x plus h squared. If you FOIL that out, you'll get x squared plus 2xh plus h squared. Now I'll distribute that negative. So this is f of x plus h. Now we want to subtract f of x. And if I subtract f of x, I'm subtracting this whole thing. I'm going to be subtracting 4x, and I'm subtracting a negative x squared, so I'm going to add x squared. So our expression for f of x plus h minus f of x is equal to 4h minus 2xh minus h squared, because the 4x and the minus 4x cancel, the minus x squared and plus x squared cancel. So this is sort of this side work, this algebra work I'm doing that I can use to substitute into this limit that we set up. So m tan, this is the limit as h approaches 0. F of x plus h minus f of x all over h. Every time I do one of these, I write this limit out fresh like this, because I know this is something I should know, and if I write it every time I need it, then it's unlikely that I'll forget it when I need to know it. So it is a limit. I'm going to make sure that I rewrite lim. I carry the lim through my calculation here. The numerator we just found, so this is 4h minus 2xh minus h squared all over h. Now look, take a look at this limit that we have now. Note that in the numerator every term has a factor of h. That's a very good sign. And when you're doing this, setting up this limit, and your function is a polynomial, it will always be the case that every term has a factor of h right here. And if it doesn't, then that means there's probably maybe an algebra mistake earlier on, and we should find it. So we have a factor of h in every term. Let's factor it out. Now we can cancel the h. At this point, we're getting pretty excited, because if there's no h in the denominator, now it's no longer a problem to let h approach 0. I've got an h in the expression, but that's fine, right? H can be 0 in this expression because it wouldn't make me divide by 0. So now if we let h approach 0, it is at this moment I no longer need to write lim. I can let h approach 0, and we get 4 minus 2x. This is the expression for m tan, for the slope of the tangent line. And this will give me the slope of the tangent line at an arbitrary value x. So the rest of this example, we did most of the work. The rest of this example, they asked us to calculate the slope of a tangent line when x is -1, when x is 2, and when x is 3. So let's finish this up. When x is -1, m tan is, I'm just going to put -1 into that expression, 4 minus 2 times -1, and that gives us 6. At x equals 2, our slope is 4 minus 2 times 2, which is 0. And at x equals 3, our tangent slope is 4 minus 2 times 3, or -2. Now we can actually do a little bit more. I mean, we finished the example and what they've asked us to do, but it'd be great to maybe just make some observations or predictions on what we might expect to see when we look at the graph. When x is -1, the tangent slope is 6, positive 6. So that means that we would expect the function to be increasing at that point. At x equals 3 over here, the slope is -2. It's negative, and we would expect at this point in the graph, when x is 3, we would expect to see the graph is decreasing. And in the middle, we have this 0 slope. So a slope of 0 is horizontal, perfectly horizontal. And so this is neither increasing nor decreasing. And we might expect to see either a bit of leveling off at that point. I'm going to throw the original function into the calculator to look at the graph. The original function is 4x minus x squared. And let's see, my window's a little bit wonky here. I'm going to just go to the standard window, -10 to 10. And I think what I'll do now is zoom in a little bit. I'll let x go from -2 to +4. So I'm going to hit window, x min -2 to +4. Oops. So now let's look. Okay. So at -1, here we are, we could see that the slope, the function is increasing. At 3, the function is decreasing. At 2, this is where we have a peak here, right? So as it turns out, that this maximum value at the vertex of this parabola, this is where the tangent slope is 0, and that's sort of how that 0 tangent slope shows itself in this graph. All right, let's try another one. This time, we're going to find the expression for the slope of a line tangent to the curve y equals x cubed plus 2 for the arbitrary point xy, and then we'll use it to find the slope at a value. So our function f of x is x cubed plus 2. and we want to find the expression for the slope of a tangent line. So that means that we're going to have to do the same thing, right? We're going to need to get an expression for f of x plus h minus f of x. So let's start building that up. We're going to get the expression for f of x plus h. This is x plus h cubed plus 2. Now, of course, we can't just do a simple foiling, right? If we're cubing that out, we've got 3 factors of x plus h. So I'm going to do a little bit of an aside here and talk about evaluating, or expanding, I guess I should say, expanding x plus h to the n. Okay, and what we need in order to help us do this is Pascal's triangle. Pascal's triangle starts up at a 1. That's the top row, is just a single 1. And then at the bottom, or at the next row, we have a 1 and a 1. Our next row has 3 values. Every row starts with a 1. And then you get the next entries by adding these together, so that's a 2. Every row ends with a 1. Our next row is 1, 3, 3, ends with a 1. Then we have 1, then we have what, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And this could go on infinitely, right? Pascal's triangle has however many rows as we need it to have, but we just sort of build it in that way. So when we expand, let's say I wanted to do x plus h to the 4th power. I'm going to leave space for some unknown coefficients, but I'm going to start with x to the 4th, some unknown coefficient. Now in my next term, I'm going to decrease the power of x by 1 and add in an h to the 1st. And now the powers of x are going to keep decreasing as the powers of h increase. So we have x squared, h squared, x to the 1st, h cubed, and then our last term is just all h's, h to the 4th. Note that in every term, these exponents always add up to 4. And now the only thing we need to figure out is what are our coefficients. And if we wanted x plus h to the 4th, we use the row of Pascal's triangle that begins 1, 4. And we have 1, 4, 6, 4, 1. So that allows us to expand these with doing a lot less algebra. And in the example that we're currently working on, back in the notes, we wanted x plus h cubed. So I'm going to start out with all x's, x cubed, and then I'm going to have an x squared h to the 1st, and then I'm going to have an x h squared, and then finally h cubed. And because this is cubed, I'm going to use the row that begins 1, 3, and my coefficients are 1, 3, 3, 1. So let's bring this back to our notes. So this is x cubed plus 3x squared h plus 3xh squared plus h cubed, and then plus 2. So there's f of x plus h. And in the limit, we're going to have to subtract f of x. So let's subtract f of x. And if we are subtracting f of x, then we are subtracting x cubed and subtracting 2. So minus x cubed minus 2. So f of x plus h minus f of x up here we could see the x cubes cancel and the 2's cancel, So we are left with 3x squared h plus 3x h squared plus h cubed. There's our expression for f of x plus h minus f of x. And now we're ready to set up the limit. So our m tan, this is the limit as h approaches 0. F of x plus h minus f of x all over h. This is the limit as h approaches 0. 3x squared h plus 3x h squared plus h cubed all over h. We could factor out an h from the numerator. Now we can cancel those h's. At this point, right, we're starting to feel pretty satisfied with ourselves because since we were able to cancel that h, in this next line there will be no problem letting h equal 0. And if we let h equal 0, then of course this goes to 0, that term goes to 0, and we're left with 3x squared. There's our expression for the slope of the tangent line. And the last thing they've asked us to do is evaluate this tangent slope at x equals a half. So 3 times 1/2 squared is 3/4. I guess we could say that our function is increasing at x equals a half.